Okay, looking at the reduction of carbonyl or of carboxylic acids and their derivatives. RCOZs are called carboxylic acid derivatives because they remind you of carboxylic acids. Carboxylic acid, RC double bond O OH, an electronegative oxygen. RCOZs, the Z is the OH if it's a carboxylic acid. It's OCH3, esters, amides, acid chlorides. You got an electronegative thing. We're going to find out carboxylic acids are quite useful and they're quite stable, and so these other groups are called carboxylic acid derivatives, the RCOZs. So let's look at this. Lithium aluminum hydride, as we said, is a very powerful reducing reagent. It's a beast, and it will reduce everything as far as it can. So we look for milder reducing agents, and the two that really work nicely are diisobutyl aluminum hydride, which here's if you're writing it out, and that's just a beast to say. And here's the drawing of it, diisobutyl aluminum hydride. We just call it dibal-H. Yeah, dibal-H. Remember, dibal-H, a milder reducing agent. Another one is lithium triterbutoxyaluminum hydride. Oof, look at that beast right there. That will work. In the literature these days, it's an old school reagent. We tend to see dibal-H a lot more because it's old school and people know it. And it's a lot easier writing dibal-H than that. But either one of these are milder reducing agents. So, if we look here, if we have an acid chloride, an ester, if we look at this acid chloride or acyl chloride, means the same thing, and you add lithium aluminum hydride followed by water, never at the same time, it will explode, but lithium aluminum hydride followed by water, we're going to reduce the acid chloride to the primary alcohol. If we use dibal-H or our lithium triterbutoxyaluminum hydride, it will reduce it to the aldehyde. Lithium aluminum hydride, very, very powerful. We'll see the mechanism. It reduces the acid chloride to the aldehyde, then reduces the aldehyde to the primary alcohol, and you can't stop it. Our milder reducing agents, you can stop at the aldehyde. Can you see how it's going to add one hydrogen here and kick off the chlorine? You will see it in the mechanism that we will go over. If we have esters, lithium aluminum hydride takes an ester, boom, primary alcohol again. Dibal-H, milder reagent followed by water, stops at the aldehyde. Okay. And when we look at the mechanism, we can see why aldehydes are formed, because this is an example of nucleophilic acyl substitution. Our nucleophile is the hydride, H-. The lone pair, or the bonding pair here of the hydride attacks the partially positive carbonyl carbon, double bond breaks, pi bond breaks. Pi bond reforms to kick off the electronegative Z atom to make the aldehyde. So if you're dealing with dibal-H or the triterbutoxyaluminum hydride, they are mild reagents. That one hydride will attack and leave the aldehyde here as a substitution product. But if you're using lithium aluminum hydride, we know that it's going to it's a powerful reagent. It's like, well, I'm a powerful reagent. I see some aldehyde. I'm going to take him out. And then this lone pair, or the bonding pair here, will attack this carbonyl again. Double bond breaks. Now we've got all carbon-hydrogen bonds, no Z group to get rid of, so water is going to protonate that to make the primary alcohol. So there's the deal. Our milder reagents, hydride attacks the carbon, kicks off Z, and that gives us the aldehyde, and they stop at the aldehyde for acid chlorides and esters. Lithium aluminum hydride is too powerful. It just can't stop at the aldehyde, and it's going to take it all the way down to the primary alcohol. Okay. So, what about our carboxylic acids and, say, amides? These are pretty, they're less reactive. We've got bad leaving groups here. Well, carboxylic acid, lithium aluminum hydride, we just showed primary alcohol. Carboxylic acid and dival H, no reaction. Carboxylic acids are fairly stable molecules, and dival H, these milder reagents, are just too mild to react with them. Okay, yeah. So, if we look down here, RC double bond O NH2, we've got our amide here, and R2, lithium aluminum hydride, changes it down to the primary amine. So if you had, say, cyclohexane, carbonyl, NHCH3, lithium aluminum hydride, you're just going to add 2 hydrogens to this carbon here, and you get your primary amine. Don't worry so much about this mechanism. You've got a lot to learn, a lot of mechanisms to learn this semester, so this is one that I don't care you know so much about. Just as it goes through the mechanism here, as you look through it to get a general idea of what's going to happen here, note we make this beast right here, where you've got a carbon double bond nitrogen here. This is called an imine. Okay, RCH, or it could be RCR here. Double bond N is an imine, and we will see these imines again. Something to note, we're going to get to it later. Carboxylic acids are very stable. They don't like to react. We're going to find out that they give us trouble all the time because one, they're stable, and 2, this hydrogen is acidic, so it's the only thing that really likes to react. But we like to use them and we like to make them because of this. There's a nice reaction. If you take a carboxylic acid and add SOCl2, thionyl chloride, what you find is you will make the acid chloride. This is a good reaction to have in your memory. Keep this in there. Recall from Organic 1 that we changed alcohols into chlorides using SOCl2. Take a secondary alcohol, you can make it a secondary chloroalkane using SOCl2. That's what SOCl2 does. Takes OH and makes it Cl, even with a carboxylic acid. So this is very important because we're going to take an unreactive carboxylic acid, react with thionyl chloride to make a very reactive acid chloride. And we'll discuss this much further in subsequent chapters. Okay. So now that we've done some reductions here, let's look at some oxidation reactions. And we covered most oxidations in Organic 1 in Chapter 12. Recall you can use our chromium-6 reagent, CrO3, sodium dichromate, potassium permanganate. Note these chromium reagents have chromium in the +6 oxidation state. This manganese is in the +7 oxidation state. Very, very positively charged metals that really, really want electrons. We'll take electrons from pert near anything. And so if you take electrons away from something, that the thing gets oxidized when it loses electrons. They're all very strong oxidizers, and they're not very selective. But then came Tollens reagent, and we call this a Tollens test because it's just so cool. What Tollens found is if you take a molecule, and here we've got an aldehyde and OH on there, an alcohol on here, and you react it with silver 1 oxide, so that's Ag2O, in ammonium hydroxide, you can oxidize the aldehyde to the carboxylic acid, but it leaves the alcohol alone. This set of reagents, Tollens reagents, oxidizes aldehydes to carboxylic acids. That's all it does. It does not oxidize alcohols to ketones, which means this is a great way to see if you have an aldehyde in your molecule, why we call it the Tollens test. And the reason it's so great is because the other product of the reaction is solid silver. And solid silver, if it's not attached to anything, is kind of a grayish color, well, silverish color. And if it's in glassware, it forms a silver mirror on the glass. So this is just a fun and excellent way to tell if you have an aldehyde in your molecule. You're running a reaction, you've got a product. Well, what is it? I don't know. It may be an aldehyde. You just take a little bit of it, put in some of this Tollens reagent, a couple of drops of Tollens reagent. If it turns gray, you know you have an aldehyde, because that's all Tollens reagents reacts with are aldehydes. So that's a really nice and very definitive test for alcohols in your molecule. Or excuse me, of aldehydes in your molecules, because if there's an alcohol in there, Tollens reagent will not oxidize that alcohol. All right. I'm going to cut this video off here because the next thing I want to discuss it all together, and it's a little lengthy, organometallic reagents.